Okay, so now we have the concept of a device. You can envision it being a server, a mainframe, whatever you want, but we've got the concept of a networking device connecting to a cable, and that networking device says, okay, I'm running the Ethernet protocol, which means I'm not the only one on this cable. There could be an unknown quantity of devices on the same cable as me. I don't know. Right? Before Ethernet, I did know. Before Ethernet, back in 1969, I just knew it was me and one other mainframe, and that's it. Well, we can't make that assumption anymore. Now that this device is running Ethernet, he says, I'm in a broadcast domain. It could be me and one other guy, or it could be me and 20 guys on this cable. I just don't know. So now the developers of Ethernet said, okay, well, so when I'm communicating on this cable, as I communicate, I could do it in one of three different ways. I could do a broadcast, which means as I'm putting my ones and zeros on this cable, it's meant for everybody. Now in the case of a broadcast, really, we don't even need any kind of an address, right? I mean, if Ethernet had been developed, let's just imagine this. If the developers of Ethernet had said, okay, anytime anything goes into an Ethernet frame, regardless of what it is, it's gonna go to everybody. It's just always gonna be like that. Then they would not have needed an address at all. There wouldn't be a need for it. But clearly, that's not the way it works, and that doesn't really make sense to develop it that way. So they said, okay, we could do broadcast. There might be a need for that. Or we could do unicast. You know, maybe when someone's putting something on the wire, it's going to be meant for one other device on that same wire. So they said, okay, in that particular case, we need an address. So when this data is being put on the wire, it needs to have a unique source address of where it came from, and it needs to have a unique destination address of where it's going to. And also keep in mind right here, now we've got devices that have two addresses that they're using, right? Because remember, IP came first. So I've got this device connected to a network that for several years has been utilizing this 32-bit number, this IP number. And the first 8 bits have been the network. The remaining 24 bits at the end have been my own unique host identifier. Now, in addition to that, if I'm coupling Ethernet to IP, if I'm saying, okay, well, at layer 2, you're now running Ethernet, now in addition to an IP address, I have to also utilize a second address, a MAC address, a layer 2 media access control address, which is what Ethernet uses. So the developers of these addresses said, okay, we need to structure the address in such a way that if I'm sending it to everyone as a broadcast, both my layer 3 IP address and my layer 2 MAC address need to reflect that. I need to come up with some kind of address that says this is for everybody on this cable. And I'll show you in just a second what that looks like. Then they said, okay, what if I'm sending it directly to Bob's computer? Bob's computer is on the same broadcast domain as me. Well, once again, at layer 3, I need to say in the world of IP that this came from my IP address and it's going to Bob's IP address. And at layer 2, in the world of Ethernet, I need to say it came from my MAC address and it's going to Bob's MAC address. And then the third form of communication was multicast. Multicast is the concept where, okay, on this cable, this Ethernet broadcast domain, let's say there's 100 devices, okay, 100 PCs and servers and stuff. Now, I am going to start transmitting data on this cable, and of the 99 devices on this cable, in addition to me, maybe 6 of them need this information. Well, broadcast is not appropriate because I don't want to go out to everybody. And I could do unicast. I could take this information, send one copy of it to, Sally's unicast address, copy it again and send another copy on the cable to Tom's unicast address. But that would put a lot of burden on me to make multiple copies of the same data and send it out there multiple times. So they came up with a third alternative, which is called multicast. Multicast is the idea that just like unicast or broadcast, I'm putting one copy of the data on the wire. I'm just sending out once. But at the layer 3 address and at the layer 2 address, It has a special address that says this is going to a group of people. It's not going to everybody. It's not going to just one person. It's going to a group of people. Now, what's kind of interesting is that in the world of multicast, the sender of the information, which is me, the one who's transmitting the information, really doesn't know and doesn't care how many people are in that group. It's sort of like broadcast in that regard. When you put a broadcast on the wire, you don't know who's out there. You don't know who's going to get it or how many people are going to get it. You don't care. You're just saying, hey, everybody, whoever's out there, this is for everyone. Multicast is kind of the same way where you're saying, okay, hey, I'm putting some data on the wire. If there are any interested individuals, here you go. So it's actually, in my example of the 100 people on the wire where there's 6 people actually want this and the other people don't, those 6, I have to use a special address at layer 3 and layer 2 called a multicast address. It's formatted in a unique way. It's still 32 bits at layer 3 and it's still 48 bits at layer 2. But the structure of a multicast address is such a way that the receivers, those 6 people, are looking for it. They're saying, okay, I'm looking as data comes in the wire, as I'm seeing the electrical voltage going across, I'm saying, okay, well, see, I'm running Ethernet, which tells me that, 60 bits into it is where I will find the destination MAC address, who it's going to. Now, if I'm a unique individual, I will say, okay, well, if that destination MAC address is broadcast, I've got to pick it up. I have to look at it, see if I'm interested. If that destination address is mine, my own unicast address, well, clearly, I have to pick that up and look at it. But now I'm looking for a third type of address. If that destination address is a special multicast address that I have been told I need to look for, I will pick it up and process it. So in the world of multicast, you've got this concept of senders and receivers. You've got one sender who's sending one copy of the data, and you've got potentially multiple receivers. And it's really the job of the receivers to somehow discover what that special address is going to be and for them to start listening to that. Now, that's a whole different world. We're not going to get into that today about, well, how do the receivers discover that special multicast address? How do they know what to look for? Well, there's various different ways to do that. But the idea is what makes multicast different from broadcast is that it's only a select group of people that's actually looking for that data. In a broadcast domain, everybody's still going to see it, because remember, in the broadcast domain, the concept is you put something in that wire, that electrical energy is seen by everyone on that wire. The question is, what people, when they see that electrical energy, are going to ignore it? What people are going to process it and say, this is for me? In the case of multicast, it's a group of people. So now we've got this concept of devices having 2 addresses, a layer 3 IP address and a layer 2 MAC address. And now we know that those 2 addresses can be formatted in one of 3 different ways, as broadcast, unicast, and multicast. Now, when it comes to network software applications, as we can see here, they fall into 2 different categories. There's some network software that just makes the assumption, like ARP, the Address Resolution Protocol, that when you invoke the software, when you tell it to start up, that software will say, okay, I am designed in such a way that I am only going to talk to people in my own broadcast domain. I don't even know about other broadcast domains. I don't even know they exist. I'm just going to talk to people in my broadcast domain. So those types of software applications, technically, they don't even need IP. All they really need is a layer 2 address if they're going to talk in their own broadcast domain. But most software falls into the second category, those capable of intra or inter broadcast domain communications. So a common misconception when people are first starting to learn about IP is they think, okay, well, an IP address then is equivalent to a broadcast domain. I've got one cable here, and so that's going to be one network. So that's going to need an IP address, need a network address. And then I've got another cable over here in a different building. That's a different broadcast domain, so that's going to need a network address. So people think, okay, they're equivalent. IP address equals broadcast domain. And that's not quite the case. So as we see here, IP is used to address networks. Those networks might take the form of a broadcast domain if they're using Ethernet or token ring, or they could be using some other protocol that makes it a point-to-point network like HDLC or PPP. The main idea is that whenever you have a cable and you expect IP packets to go across that cable, either end of that cable needs to know that this is part of a network. We need an IP address to represent this network, whether it be point-to-point or a broadcast domain, a collection of Ethernet devices. So an IP address, we know that the original developers of IP, they structured it in such a way that it had two parts to it. The first 25% of that address, so I guess if you're looking at this would be the left here, the first 8 bits represent the network. So let's just say if we're talking about Ethernet, that represents the broadcast domain. Everybody on that Ethernet segment has the same 8 bits in common. They're part of the same group, okay, part of the same clique. And then the remaining 24 bits at the end are unique on every single host. So if we're talking about a broadcast domain, if I'm talking about an Ethernet segment that's got 100 devices on it, because they're all part of the same broadcast domain, they can all see each other's electrical energy from a layer 3 perspective, from an IP perspective. It was originally designed that they would all have the first 8 bits in common. They'd all have the same 8 bits. They're all part of the same group. But then of all those 100 devices, the remaining 24 bits would have unique patterns. Each device would have its own unique, what they call host address or host bits. Okay, so we have devices that have 2 addresses, a layer 3 IP address and a layer 2 address. Let's just say it's a MAC address. And some application running way up here, at, layer 7 of the OSI model. So that application gets invoked, and that application says, okay, I need to hook into IP so I can actually get out of my chassis, get out of my box, and put some data on the wire. Okay, well, we know that as far as layer 2 is concerned, the MAC layer, the data link layer, let's say, we know that that application has one fundamental question it has to answer as far as networking is concerned. It has to answer the question, the destination I'm trying to reach, the person I want to talk to, are they on the same wire as me, are in the same broadcast domain, or are they not? Are they in some other broadcast domain? Meaning that when I put my electrical energy on this wire, they can't see it because they're not on this broadcast domain. So every application that's network aware has to answer that question. So if the application determines that, okay, the destination I'm trying to reach is in my broadcast domain, I can talk to him directly. He will see my electrical energy as soon as I start putting it on the wire. Well, that application can't skip past IP. You might think, okay, well, in that particular case, we don't need to use IP at all. Let's just skip past it and just go straight to layer 2 addresses. Can't do that. If a system like a laptop or a PC is running both IP and Ethernet, you can't skip past IP. So when you put your data on the wire, you're going to have an IP address in there and a MAC address. Now in this particular case, if the person I'm talking to is on my wire, the IP address is kind of irrelevant because I'm talking to them directly via their layer 2 address. If they're on my wire and now I discover what their layer 2 address is, so as I'm transmitting my bits at layer 2, their NIC card can say, oh, this is for me. There's other people seeing it, but this is for me. And once my NIC card identifies that as a unicast transmission, it doesn't really need to see the IP address, but we can't skip past it, so the destination IP address will be in there as well. Now, let's say I'm trying to talk to somebody that's not on my wire, somebody that's on a different broadcast domain. Well, same thing. When I put my data on the wire, I can't skip past layer 2. Even though the person I'm trying to talk to technically can't see my layer 2, they can't see my electrical energy, I can't just take data, address it with the destination IP address of the person that's 5,000 miles away, and put on my cable. Because my cable says, well, wait a second, I'm running a layer 2 protocol. I'm running Ethernet. And the rules of Ethernet state, I need a layer 2 address. So when you're talking to somebody that's not in the same broadcast domain as you, you say, okay, well, what do I use as a layer 2 address? Because they're not on the same broadcast domain. And this is where the concept of a default gateway comes in, a router. A router is a device that should know not only the broadcast domain he's connected to, which is the same one you are on, but he should also know about other broadcast domains. So he's like, an intermediary device. So in the case of that, if my application says, okay, let's see here, the destination I need to talk to is not on my broadcast domain, it's somewhere else. Then the destination says, okay, here's what I need to do. At layer 3, I will source the data from my IP address, from my unique 8-bit combination of my network. And then at layer 3, I will put the destination IP address as the destination I'm trying to reach. And he has a unique 8-bit combination of bits. Then we send that down to layer 2. At layer 2, I will put the source address as my own NIC card's MAC address, my layer 2 address, and the destination address will be, okay, well, who on my broadcast domain can help me get this data to where it needs to go? The router, the default gateway. So at layer 2, the layer 2 address will be the router. And this is, for those of you who are studying for your CCNA, this is a foundational thing you need to be aware of, is that when you've got a device running Ethernet and IP, whenever it puts data on the wire, you will always see 2 addresses in that data. You'll see a layer 2 MAC and a layer 3 IP address. Both of them will be in there. Now, if the person you're trying to talk to is on your wire, is in your broadcast domain, the destination layer 3 address will be the person you're trying to talk to, and the destination layer 2 address will be the person you're trying to talk to. It's being unicast directly to them. But if the person you're trying to talk to is in a remote broadcast domain, which might be a dozen feet or 2,000 miles away, at layer 3, nothing changes. At layer 3, it's still your source IP address going to their destination IP address. What changes is layer 2. At layer 2, because you can't talk to them directly, you use your source MAC address and you use your default gateway's MAC address as the destination. And the assumption is, okay, as I'm putting the electrical energy on the wire, the default gateway will say, oh, that's for me. I see my MAC address here. And then when he gets that Ethernet frame and he removes it and he goes up to layer 3, that's when the router will say, ah, well, at layer 2 it looked like this is a unicast transmission for me, but at layer 3 it's not. At layer 3 he says, oh, the destination IP address is not one of mine, it's somebody else's. And now it's the router's job to forward that data into another broadcast domain, and it'll hop through various broadcast domains until it reaches the destination broadcast domain. So this is what we're talking about here. On the top we've got one broadcast domain, which is called LAN 1. And so, in the original days of IP, we reserved the first 8 bits for that network. And so it might be, 7 zeros and a 1. On the bottom, we have LAN number 2, a second broadcast domain. So that needs a different unique group number, a different unique network number. So how do computers and mainframes and stuff actually see this? So we know that a MAC address is, in binary, 48 bits long. So there's 48 bits right there. An IP address, a little bit shorter, 32 bits long. So what does a computer see when it looks at incoming data? I'll go ahead and expand this a little bit for you here. So there's the source on the right, sending data to the destination on the left. What's coming in is just a string of thousands of ones and zeros. So where are these addresses in all this? Well, if that destination device is running the Ethernet protocol, he's going to say, okay, the first 64 bits that I saw coming in is a bunch of Ethernet stuff. Basically what we call the preamble. Then from bit 65 to bit 112, that's the destination MAC address. And then bits 113 through 160 are the source MAC address. Now hopefully nobody will ever actually ask you to do this, but if someone said, hey, I'm going to give you a piece of paper that's got 2,000 bits in binary written on it. Can you tell me what the destination MAC address is in this long string of bits? This is how you do it. You'd say, okay, well, if this thing is Ethernet and means that somewhere in here is a MAC address, you would look right at bit 65 and go from 65 to 112. And that would be your destination MAC. And then 113 to 160 would be your source MAC. And then Ethernet says, okay, I've got another 16 bits of Ethernet stuff and I'm done. So as far as Ethernet is concerned, all of that is layer 1 and layer 2. So that's layer 2 stuff that Ethernet interprets. Then once Ethernet is done, it removes all of that stuff, sends it up to layer 3. And if we're assuming that IP version 4 is going to run at layer 3, now IP version 4 starts by looking right here. This is what IP version 4 sees. And it says, okay, the first 96 bits are IP stuff. So, if you ever do a Google search on an IPv4 header, you'll see that IPv4 actually has a lot of bits it needs to look at before it ever gets to any address. It has like an IP version field, IP header length, whole bunch of stuff. So it's 96 bits of stuff that IP looks at. And then at bit number 273, that's where we see our source IP address. And because an IP address is 32 bits long, that goes from bit 273 to bit 304. And then from bit 305 to 336 is the destination IP address. And then there's more bits beyond this that are other IP stuff like IP options. And then you're going to have a whole string of bits after that, which is what TCP looks at. And then you're going to have a whole string of bits after that for, what FTP looks at or Telnet looks like. So really, a simple packet of like Telnet or email is going to be thousands of bits long. But within the first few hundred bits is where you're going to see your MAC addresses and your IP addresses encoded. So that's what your computer sees.